Welcome everybody. So the talk will be in English. It's going to be a short introduction to Microsoft Orleans and to show you how you can get started with it and what the framework is. So my name is Eltjo Kraai and I'm a member of the .NET Barcelona Community. And I work at Cotecna in my daily life. Now, first of all, what is the Orleans framework? So if you look at the website, it says that it is a cross-platform framework for building robust, scalable, distributed applications. So, well, the goal is to understand a bit how this miracle can be achieved. So first, a bit of history. It was created by the extreme computing group Microsoft Research, and in 2011 they used it to handle the massive amount of traffic for the cloud services of Halo 4. So they needed something that scaled really well, because just before the release of the game there was nobody playing it, and then they had hundreds of thousands of players at the same time, so that was a real technical challenge. They open sourced it in 2015, and you can find it on GitHub. So Orleans today is widely used in production, also by Microsoft itself. All these services that you see there, they run somewhere, they use Orleans in the systems. They depend in some way of Orleans. Since NET Core 3, Orleans, the versioning has been aligned with the rest of the .NET versions. Since version 8 there is official support from Microsoft, and version 9 was released almost immediately after the framework version. So it's really becoming a first-class citizen of the .NET ecosystem. Now, a few fundamental concepts. So there are two that we need to know about, and those are the grains and the silos. And the relationship between them is exactly what you expect. A grain is a small thing, and there are a lot of them in a silo. First of all, what is a grain? So this is the fundamental building block of an Orleans application. It is something that is known as an actor, and an actor was a concept from the 70s. To deal with highly concurrent applications that have very much an isolated state from each other. So many objects that have nothing to do with each other, and they consist of identity, behavior, and state. The innovation brought about by Orleans is that it is a virtual actor model, and virtual means that they always exist, meaning that we don't care about instantiation of whereabouts. We just call it, and everything happens behind the scenes. Now, this kind of object that you see there, a grain, something with an identity and a behavior and a state, that is something that corresponds very well to a concept from domain-driven design, which is the aggregate root. Something that has well encapsulated behavior and an identity. So it's also in that context that this is an interesting concept. Now, the life cycle of a grain. A grain gets automatically instantiated whenever it is called. It can process messages when active in memory, and after a configurable idle time it gets deactivated, and the optional state is persisted. So the second fundamental concept is a silo, and grains are managed by silos. So each silo, a cluster of Orleans machines that you can scale, consists of many silos that intercommunicate and divide the workload. All grains are managed by the silos, so their entire life cycle, and one server typically hosts one silo. Now, the structure of an, by the way, if there are any questions meanwhile, don't hesitate to ask them. I'd be happy. That's okay. So that was quick, but thank you. The structure of an Orleans solution. So on the one hand side, we are building a backend application. So we have a web API, and usually we don't call our functionality directly in the application or in the controllers, but we use the application layer. And the application layer orchestrates the domain. So it instantiates domain objects that we want to perform manipulations on. But in an Orleans application, those domain instances is what we want to scale. So they live in silos. And for the web API to be able to call our silos, we need a layer of abstractions. And the packages that we need for that is a client package on the application layer, a server package on the silo, and an SDK on the abstractions layer. So let me show you how we can build I hope you can see the screen. You can read it? Yes, I think so. So we have here a very small application. It's very trivial, but I skipped the application layer in this case. But you can see that we have as the package here the audience client. We have our silo that has our audience server package, and our domain consists of abstractions and the domain package. And our abstractions package has a dependency on our SDK. Now, this is a plain web API that you see here. This is the program.cs from a web API. And to connect this to our audience cluster, there's not a lot that we need to do, but we need to add an audience client to the host. And then we need to specify in a client builder that we want to use a local host cluster for debugging. So in production, of course, you're not going to use a local host cluster, but use a cluster that you define elsewhere. And so we need the client builder dot use local host clustering. And that is all we need to do to connect the front end with our cluster. Now, for the silo, we have another separate project, and that is this. So starting from a plain old console application, because this is in the end nothing else than a console application, we can create well, a host builder in the usual way. And that is host, let me see this. So let's create default builder. And then again, use audience. So within this builder, we specify our options using a special silo builder. So defining a silo builder here is a lambda parameter. Then we have our host builder. Now next we need to build the host and make sure that it can get executed. So and we start our host with await host.run async. Now, of course, we also need to configure the silo builder a bit, and for that we need to build a local host cluster. So we use local host clustering. Then we want a bit of logging. That is because that's always important. So configure logging again with the same pluggable structure. You have a logging builder, and the logging builder dot add console, but we can also add application insights logging in here and all other logging providers that you want to use by simply adding another NuGet package. Now, there's one more thing that I would like to add here, and that is a project built by the community, and that is the dashboard. And now we are almost ready to run our web API on the one hand and our cluster on the other hand. So we have two separate applications that need to run, and for that we need to configure our project to use two startup projects. And we have the silo that has to start first, and then the web API that can connect to the silo. And with that, we have a working audience cluster. So if I start this program, I will show that now to you. So we have so this is the logging from our silo, And we also have a web application running, although we cannot see that very well, but I can convince you that it runs by doing some request. And you will see that it fails probably, but it fails with a 405, meaning that the web server is running. Now, the dashboard that Xavi was alluding to, that is a server that is automatically started on localhost port 8080. And that gives you a bit of information about your project and how it is running. So currently we have almost nothing in it. It's just an empty Orleans project. And you can see that we have a dashboard grain and 5 management grains that are needed by the system. And we have one silo, but if you have, obviously, if you have more servers running, then you see everything in here. So now we have everything to start building our grains. So to continue, so working with grains. So I will show you what a grain looks like, how we can pass messages to grains, and some important properties. Now, to write one of those famous grains, we need to define the interface, because remember that we need the web API to communicate to our silo cluster. So the grains are not going to be instantiated on the web API itself, but instead it's going to be a proxy object that sends an asynchronous message to our cluster. Now, these are the messages or method calls that can be performed in this simple example, but you can put much more functionality in here. One thing to notice is that we have the interface there, that is the iGrain with GUID key that serves so that each grain is uniquely accessible in a silo. Secondly, we see that everything is a task, and that is necessary because of the asynchronous nature of all message handling in an audience application. After all, the messages are never executed, or the method calls are never executed on the web API, but always in another machine on the cluster. So the grain itself, as you can see, it is a very simple C# class. It has nothing special, except that everything is asynchronous and that it inherits from the event grain. And with it, let's implement exactly this. So again, if anybody has questions,
yes.
Go ahead.
You mentioned that the communication is through a synchronous message.
Yes.
Okay, and what is using it?
gRPC calls. So the silo has endpoints that a cluster client is created on the web API that can be injected in the controllers. You will see that in a moment. And through that proxy object, every method call is translated into a gRPC call to a cluster. And the cluster does a lookup to see if there's already a grain active somewhere. If not, it's going to instantiate it. And if it's not on that silo, it's going to redirect it to another silo. And then I will also discuss it later, but then so that it sounds already familiar when I start talking about it, it gets put on a little message queue that each grain has in front of it, and then they get handled sequentially. So, but more on that later. So I hope this answers the question at the moment. You also had a question?
Yeah, my question was related to what you're saying now. So I guess, or I understand that you have to process messages inside.
Exactly, yes. Well, I have some the event details I already created, but we start with the interface. So we have a public interface event grain. So I took the domain of technical talks and events, because that is all something that you're vaguely familiar with. So we have an event grain, and we need to implement, so we are going to do two very simple methods, but we can also, for example, do a task that is called cancel event. But in our case, we are going to set the event details and get the event details. So to get the event details, get event details, so it guessed it right, and task set event details. And parameter event details. So now our interface is ready, and we can start calling it from our controllers. So as said, we have here an event controller. So if we want to create an event, that comes in here. So we need to when we are creating an event, we obviously have to create an ID. So one thing that is perhaps nice to see is that we have here the interface event grain, but we have to make it addressable. And there are a few implementations of, or a few interfaces that are also that inherit from iAddressable, and those are the grain with integer key or GUID key or string key. So that depends on the kind of ID that you want to use. So we are going with a GUID key, and I need to remove an A there, I see. So now in our event controller, we need to create this ID. So var ID equals GUID.new ID. Let me uncomment this line. And we can create a new grain. Now we can create the proxy object that is used for communicating to the client. And for that, we need a cluster client. So if we create a constructor here, go there and inject the iCluster client. Then we can use that cluster client to get a reference to that grain. And that is event grain equals cluster client dot get grain of type iEvent grain, and with the ID that we have here. Now here you see the why these are virtual actors, because we just pretend that it exists already. We are just calling it, and it will get instantiated somewhere. Now in this line of code, it will not be created yet. It will not be instantiated yet. It's a synchronous call, as you can see, but it's just, this constructs the proxy object that our web API is using to call the messages on a silo. So now getting those, now we can set the details for this event grain. Event grain dot set event details, and we pass the event details as a parameter. Now this looks like an ordinary method call, but this is in fact a message that's going to be sent on the line. You can see that it's complaining with a little green line there, meaning that it wants it to, it's an asynchronous call. So we are going to await it. And after the construction of it, we are going to return to our to the client of our web API the ID. Now, let me also quickly implement the update. So this is almost the same. We don't need the ID there, and we also don't need to return it. And we also have a get endpoint in here. So let me also implement that. And here we return wait event grain dot get event details. And so we have implemented a create, a put, a post, and a get endpoint to do some CRUD operations of our on our grain. Now we don't have an implementation yet, and that's what we are going to do now. So we have to add a new class. Oh, what did I do? No. By the way, there is full support for, in the latest version of Orleans, there's full support for Aspire. So, here, let me get rid of a bit of crap here. So we have we create our plain old C# class to implement a grain. We need to inherit from the iEvent grain, implement the interface, and well, the cancel event I'm not going to implement, but the get event details. We are going to create a private variable that is private event details underscore event details equals you're going to make it nullable, and we are going to for getting it, we are just going to return it immediately. So again, because this is a message that goes over the line, you need to make it asynchronous. So we are returning not the details immediately, but we are going to wrap it in a task. From result. And we simply put in here the event details. And if they don't exist yet, we're going to throw an exception. So now that is the get event details. Now the set event details, that is even simpler. Event details equals event details. And we have to return a completed task in that case. So as you can see, we now have a very simple class. It's plain old C#. And the only difference that you have with how you would implement it in any other application is that even trivial method calls that are immediately on private variables are still have to be asynchronous. Now, if we run this application, then you will see a big fat exception, I think. Oh, we have build errors. So I mentioned that an actor, a combination of ID, behavior, and state, looks very much like a DDD aggregate root. And as we are talking about domain-driven design and the technical patterns of domain-driven design, you see that in our event details, we have very simple primitive types. We have a GUID that is the ID, we have a string that is a title, and a string that is a description. Now, as an example of using value objects in DDD, where you have an internal validation of every business object that you use, I have created an object that is called event title, and it's just a wrapper for this simple value, but it has a method that throws whenever the state is invalid. And in this case, it just checks that it has a reasonable length and nothing more. But I would like to show you that. So one of the things that I would like to show you is that Orleans is very much compatible with the technical patterns of domain-driven design. So in that sense, I'm going to use the event title here. And so it is complaining here that it is. So. And now I think I also need to add a package in here, but the line is a bit long, so we don't see it, but we need to import a namespace. So if we now run the project, it will compile this time, but we will still see a big fat exception. And this is interesting because what you see there is that we have unserializable or uncopyable types which are being referenced in grain interface signatures. Now, and there you again see one of this property that these method calls that we are doing in our controller are not simple method calls, but they are messages that are sent asynchronously over a network. And for that, all those parameters need to be serialized. So in Orleans, there's a built-in serializer, which is efficient and also very version tolerant. And to make this, our event details that is passed as a parameter in those method calls serializable, we need to tell Orleans on compilation to generate a serializer using the C# code generators. And we need to provide some attributes here. And those attributes really serve for versioning. So if you have a new version of a grain somewhere that has a new parameter, that new parameter will be ignored by other grains or by silos that don't know yet about the implementation, and it will be used by silos that do know about the implementation. So this is mostly for rolling updates. Now our project should be able to run.
Binary serialization or is binary or other kind of?
I think it is configurable. I have to say that I do not know what it uses for the gRPC calls. I suppose binary, since it is most efficient. So yeah. So yeah, thank you for the question. So now we have it running. So we can take a look at our silo, and we still have nothing. But if we now call the endpoint to create an event, you can see that we have immediately an event grain. And if we call it a few more times, you can see that we have 4 event grains, and they stay in memory. So they stay in memory for about 2 hours. So if they are not called, they will stay in memory for 2 hours, and otherwise as long as they are used. So that has as a big advantage that you are continuously caching every highly contended object. Now, to show you some other properties here, well, let's first test that everything is working fine. So we have we get an ID back from the grain that we have just instantiated. So let's get it. And that works. And we can also update it by putting a 2 in the title. And that also works. Then we can so now we have a working web API. Now, to show you some of the properties that are interesting of these grains. So it's important to note that these grains handle all messages that are coming in, so all method calls sequentially. So every gRPC call from the web API is when it arrives at the cluster, it is put on an internal queue before the grain and executed sequentially. So we can easily check that. So if we await here task.delay, if we wait for a few seconds in this method, and if we call the get event and this one simultaneously. So let me do the hot reload. Let's see if we are lucky. Yeah, I think so. So we first send an update event, and you can see that it is being handled now, and then we perform a get. And only when this is completely ready, because now it's doing nothing while it is waiting, but the get event is still not handled. And only when this is completely finished, you can see that it starts running the second request that came in. Now, for optimization reasons, this is not always what you want, of course, because sometimes you want to have an immediate answer, and there are options to handle that. So in our event grain, the get event details, we can tell Orleans that it's allowed to always interleave, meaning that it can it is allowed to handle the get event details simultaneously with any other object. There are also other options. That is, for example, may interleave, and that depends on the predicate. There you can decide which function, for example, it can interleave with. But we, for this demo, we use always interleave. So to see the effects, well, this is not going to work on a hot reload. So here I do need to restart the server. And something else is that we don't have any storage yet. So we will get an exception here. So we will need to recreate our grain. Storage we will hook up later. So we need to create it again. It's in the breakpoint. So we have just created this grain. We have to, and we again are going to do the get call simultaneously with the update call. So first we do update, and then we do the get call. And now you see something interesting, because now again the get event, the set event details is executed first, but now when we hit the task.delay, the thread gets freed up to do other things, just like any await async method. And now you can see that it handles simultaneously the get event. And when this is done, it again continues with the execution of the second grain. So the grain is still single-threaded. There's never more than one thread that is handling a grain. So it's a bit like JavaScript, where you have never two lines of code that are simultaneously executed. But whenever that thread is not doing anything, if you have the always interleave activated, it will be able to carry out multiple things at the same time. But note that a whole class of concurrency issues simply does not exist anymore by handling all method calls sequentially. So, to recap, so messages or method calls are more or less the same thing in an Orleans cluster, are put on an internal queue and handled sequentially, with the options of making a grain re-entrant or putting always interleave attributes on interface methods. You can make an exception for that, but still the method execution is always single-threaded. Another thing you saw that in our controllers, we do nothing to instantiate a grain, except that we tell the grain cluster that we want one. But other than that, we don't need to write any code for instantiation. And highly contented objects are always cached. You saw that in the cluster. The grains keep existing after they have been created, and they will keep in memory for 2 hours. By default, you can configure it, and you can also clean them up immediately after a method call. So here you see the example in the interface with the always interleave method. But if you want the entire grain to be able to handle everything whenever the thread is available, you can mark the entire grain as re-entrant. Any questions so far?
You mentioned that in an internal queue, you expose to the grain, and the grain, when it returns something to the client, how is returning that to the client? Is this in another queue, or at the end, you are using queues for client to server?
I have to say that I don't know the other way. I don't know how that works. I don't know the details of that. But that's an interesting question. So I have to say that I've never actually worked on a production system with Orleans. It's just that I want to do this talk because I think it's one of the most fascinating technologies we have in the Microsoft ecosystem. But please go ahead.
If you use the brackets, always in your method. I'm not formatting your result. If you use the bracket with the always implement, are you possibly introducing solutions?
Yes, and so and that is why you should be careful. So if you do simple read operations, usually it doesn't really matter if you get something just right before or right after something changed. But if you do subsequent changes, or if you have validation, or if you have a method that does several asynchronous call to other grains, for example, well, if the state changes to another state, then you get in dangerous territory. So you can introduce race conditions with that. So, but by default, as you keep the default behaviors, that whole class of race conditions doesn't exist. So, thank you. Any other question at this point? Okay, well, so let's hook up persistence, and that is something interesting because it is ridiculously simple. So in our silo, we need to plug in a persistence provider, and well, I just loaded the NuGet packages for Blob for Azure Storage, and there we can there we can choose whether to use the blob storage or the table storage. We will go for blob storage, and you have two options. You can have a named. You can see that you have a name that you can provide there, or you can use blob storage as default, which is what we will do now. But you can have multiple storage providers in one audience application. You can even store different parts of a single grain into different types of storage. So again, with following the same pluggable structure of the audience architecture, you can see that we have an options builder here. And this particular options builder, we need to create a blob storage client, options.builder.blob service clients equals new blob service client. Let me get rid of the namespace import of this and import a namespace instead. So, and now we need to provide a connection string. Now I have the Azure Storage emulator running on my machine, and I'm going to put a connection string directly in there. Of course, always use a key vault for these things. And oh, this is not what I need. Paste it well. Control C and Control V. So, and so now we have storage hooked up to our silos, so it becomes available. But now we need to tell the grain that it's going to be where it gets its state from, and for that we need to add a constructor, generate constructor. Now, in this we have in audience simple dependency injection, just like any in every grain you have a dependency injection, just like you're used to in other parts of the Microsoft ecosystem. So you can inject a logger in there, but we are going to do an I persistent state of event details, and we are going to call it details. And we need to mark it as, so the audience needs to know from which storage this is coming. So for that we need another attribute, and that is the persistent state. And here we have to fill in a name. Well, so that can be details, that's nothing special. But you can also select there the storage name. So, and that becomes important if you have multiple different storage providers in your application. So for us, we use the default one, so we don't need anything there. Now, we need to assign a field. We can clean up the state object that we previously had. Oops. And that is this one. And here we are going to use details simply, details.state. You can see that this state object contains is of type event details. And the same for the other one. Dot state, whoops, dot state. And we can get rid of the delay here because that's not so interesting. But now we are setting here the event details, and we are passing the state into the event details into the state object that is going to be persisted. But we also actually have to persist it. And for that, we are going to call the details dot write state async. And now we have, oh, it needs to be asynchronous. Wait. And now we have state, a persisted state in our application. So running it again. And creating a new grain. We create a new event. You can now see it should now have appeared in our blob storage. So let me refresh this. You see that we have a grain state, and we have a container, and this is our grain that has been persisted. Now, if we look at what this is, you can see that it is JSON. You can also choose to store it as binary, but that's obviously more efficient. But the nice thing that this is readable. And so let me put it in a slightly nicer format. And here you can see that our grain is stored as JSON in our blob storage. And I need to disconnect this, I think. Now, one thing is what is interesting, and you see the title object there, and that is our. Remember that in our application, we have here a value object. That is our title. And the interesting thing is that without doing anything extra, it becomes it serializes. Also, in here you see the values for the tags, which are audience and .NET, and it all gets automatically persisted. So you don't need to think about anything when persisting things or when modeling. So you can, with a certain carelessness, develop your. I think, can I kill this process? Is it in here? No. Thank you. Is it here? Manage notifications. No. Yeah, that was what I was going to do, but this is better. Thank you very much. So what I was saying, that as long as your the things that you are using are mildly serializable, it will work. So for quick prototyping or for domain-driven design where you want to use value objects and all kinds of built-in validations for your state, you don't need to write as an entity framework all kinds of data converters that convert a value into a column type for a database. But you can just let it serialize and it works. So it's really very convenient. Now, so that concludes the demo, because I don't think there's more time to do anything else. But to recap, we don't need to write repositories. There are several built-in storage providers, such as Azure Storage, Adobe.NET, DynamoDB, Redis, many more, also provided by the community. Multiple providers can be used at the same time. A single grain can get its state from several providers, and so it is really a flexible system. Yeah. So any questions at this point? Okay, let's continue. So the obvious problem that you have here is querying data, because we have all our information in several different stores, and we have, if you want to see which of these talks in our technical talks database are about audience, then there's no way to query for the data. You cannot open all of those blobs and check what's in it. So for that, there are several options. You can aggregate data in special grains. So obviously you can only do that as long as there's not too much data. So if you have, for example, 10,000 events in the future and you get rid of all events that have already taken place, then it's a perfectly viable solution. But if you have more than that, or if it grows without bounds, then you'd better directly write to a read model. And one of the things that we can do for that is use stateless workers. And well, stateless workers is a special type of grain that is for workloads that is not tied to any identity. We have typically one activation per silo and more if needed. And an example you see here. So if we want to write our data to a read model, then we can create a separate read model grain, which is a stateless worker. So again, if you have 10 silos, it will be instantiated 10 times, more if necessary. We have, in this case, you can see that we have a constructor that injects a repository, and in the add to read model function, we can simply add or update and make sure that a state gets persisted, after persisting state, you can also update a read model. Now, how you would use this from a grain. So this is our event grain, and you would inject a factory, because where we have in the web API a cluster client, we need a grain factory in our silos. And you can see that we instantiate a read model grain, and we simply write the details to the read model, and then we have everything up to date. So that is a strategy that you can use. So again, it fits very well with the tactical patterns of domain-driven design, where you have command query separation, and for which you can define a read model that gets updated automatically. Now, there's still, of course, a lot that we have not covered. Failures, because what happens if you fail to write to a read model, then nobody can ever see your event. So there are a number of strategies to deal with that. You can make your operations idempotent, meaning that you can execute them multiple times without problems, without causing data inconsistencies. There is full support for asset transactions in the Orleans framework, and we can also decouple. So there is an internal pub subsystem built into Orleans that can handle messages, and with that you can write to your read model keep your read model up to date using eventual consistency. For debugging, you have an in-memory stream, but for production, you can connect it to event hubs, RabbitMQ, Azure Service Bus, anything really for which you can find a NuGet library. Now, then built in, there are also timers and reminders, which are periodic triggers, and a timer can activate a grain up to 49 days after the timer is set. And there's also the option of event sourcing built into Orleans. So all of these things, of course, there's no time to cover that. So let's round it off now. So to recap, what Orleans have to offer for us is built-in persistence. So we need to write almost no code to get persistence. So no repositories. We have asset transaction support, built-in pub subsystems, schedulers and timers, load balancing, caching. What's also interesting is that we have near linear scaling from a single server to hundreds of servers. And it runs anywhere where .NET runs, which is these days Windows, Mac, Linux, everywhere. The programming model itself is what I find most interesting, since for scale, I have to say that I don't need Orleans, but what I like is that you can develop and prototype quickly without thinking about persistence. As long as your model serializes, it's okay. You don't need to write instantiation code, and the concurrency issues that you no longer have thanks to the single-threaded execution model is a very attractive idea. And furthermore, because of the nature of grains, it very strongly promotes encapsulation and boundaries on your domain model. which is which prevents the famous anemic domain model, which is always booming. And the reminders and the built-in streams and status workers, they work in many scenarios where you would normally use microservices. So you can run everything in one project. And I find that myself a very attractive idea. So thank you very much. So this is it.